Welcome, everyone. Thank you all for being here. Today's webinar is going to look at air source heat pump application guide for K-12 schools. I want to take a moment and thank our project sponsors. We had Enbridge, IESO, Train, Carrier, and HTS all participate and contribute to this project. So thank you to all of them. We also have our Sustainable Schools program sponsors with Enbridge and Train contributing there as well. I'm going to get us started here with just a little bit of housework. A reminder to use the Q&A option for any questions related to the content. We'll do our best to answer as many as we can during the webinar, and any that we don't get to, we'll answer in a Q&A document after the event. I ask if you could reserve the chat for any technology-related questions, and we'll try to address those if they come through. I'm going to hand it over to Ian to get us started with our presentation.
My name is Ian Jarvis. I'm the Executive Director of Climate Challenge Network, and Sustainable Schools is one of the programs of the Climate Challenge Network nonprofit group. We begin all our events, as those of you who follow our work will know, with acknowledging the ancestral and unceded territory of Inuit, Métis, First Nations people that we share these lands with. We have 123 people registered for this webinar today on behalf of 32 different school boards. So we've got 18 government and utility representatives, and coming from 6 of our provinces. So between us, we're covering a lot of these traditional homes, a lot of these traditional nations, and we're speaking as a virtual event, but we're speaking today from Toronto, which is again the traditional home of the Huron-Wendat, the Haudenosaunee, the Anishinaabe, and the Mississaugas of the Credit River. And as you may know, Toronto and the regions from the islands up to north of Toronto are governed by Treaty 13, the Toronto Purchase Agreement, with the Mississaugas of the Credit River. As always, the work we're doing today, your presence here, is looking to address climate change, address some of the environmental challenges that, frankly, we've created over the decades for ourselves. And it's our sincere wish at Climate Challenge Network that what we're doing today with you will make a meaningful contribution to our collective responsibility as stewards of the environment. Can we go to the next slide, please, Carolyn? So let me give you a heads up of how we plan to go through this today. We want to give you a bit of a background, which the context for most of the work we're doing at Climate Challenge Network now is around the energy transition. We need to decarbonize. We need to decarbonize quickly, and that transition from fossil fuels to low carbon, zero carbon is frankly the biggest transition in human history. So we're looking to accomplish a lot in a fairly short period of time. We're going to step onto the essential. To decarbonize, we have to first get energy efficient. We've got to reduce the amount of energy we use in order to make that transition to electrification, to decarbonization, to make it practical, to make it affordable. So energy efficiency is crucial. We're always going to emphasize that to begin with. Then the plan is to work through what are the principles of air source heat pumps, what are their challenges, what are their opportunities, how do utility rates affect both the economics and the operational practices for air source heat pump installations? How do you integrate the air source heat pump into your overall HVAC system? And as we look to decarbonize, when you're looking at these projects, what are the other things the other considerations you might make at the same time? I'll introduce our panelists in a moment, but Toronto District School Board and its just recently installed air source heat pump system. It's by no means conventional. This work is primarily today focused on rooftop units. These are multi-zone systems, but They provide a wonderful way of walking through the business case, the logic, the decision-making process. And we'll present the conclusions and recommendations. And spoiler alert, don't want to spoil anything, but our conclusion is, and we should go through the whole webinar today with this in mind. We believe that air source heat pump rooftop units are the logical choice to make right now. We'll talk about the relatively modest cost premium, but that we need to start making moves towards decarbonization. And we will be referring to air source heat pumps, for reasons we'll explain in a moment, as the best incomplete solution for the energy transition. So it doesn't get us to where we need to go, but it's a logical step that's affordable that we can take right now to cut the lion's share of greenhouse gas emissions from K-12 school operations. So that's the plan for the day. Can we move to the next slide, please? And again, those of you who attend our events regularly, they've heard this before with kind of different approaches to it, but the reality that climate change is the defining issue of our times. It's huge, it's global, it affects everybody in ways that we've only just begun to see the damage. We've got work to do. The call to action says we simply have to substantially reduce and eliminate carbon emissions that have become part of our lives over a couple of centuries, and we need to do it within decades. It's a very short, it's a very urgent timeline. The challenge always, and we'll get into this to some extent with the panel, is it's a very uncertain time. So school boards are tasked with making big decisions now, despite political uncertainty. It seems likely that whatever happens with the expected federal election this year, that the carbon tax as we've known it is going to be gone, and it's an important part of the economic case, but it's going to get replaced by something, and nobody's really stepping up yet to say what that will look like. And meanwhile, you've got decisions to make at school boards about where to go. So the economics of what we're going to talk about are going to change. Technology is going to advance fairly rapidly, we believe, over the next 15, 20 years, and that will help. But through all that uncertainty, we're making lifetime decisions today based on an incomplete deck of cards, and we have to make the best decisions we can. That's the orientation that you'll find in the discussion today. What we think is the best choice to make today, despite the lack of certainty. What we do know is we're going to build a lot more electrical generation, transmission, and distribution capacity. That is going to be extremely expensive, and electricity prices will go up. We know that the electric grid will be winter peaking by 10 years from now. So Ontario's electric grid will be winter peaking by 2035. Curiously, gas prices will rise because of declining annual demand. The gas infrastructure will stay in the ground. We believe that natural gas is an essential part of the energy transition, again, in terms of affordability. But as demand goes down, so the operating costs of the system are borne by less and less consumption. So both electricity and gas prices are going to go down. What we're going to refer back to a number of times today is the idea of the peak week, the coldest period. We're probably in it right now in Ontario. We have no good supply options. Say those are the times when there'll be most demand for gas and electricity. It will be most expensive, and we don't believe that we can switch that whole load across to electricity. It's just impractical. It's just for a small number of hours a year, the demand would be too high. We have great hopes for for storage, for electricity. All of that yet to be proven. But that peak week, we should always be looking at everything we can do to reduce peak demand during those coldest days, the coldest week, the coldest hours of the year. And air source heat pump applications aren't great for that because, as we'll talk about today, they get less and less efficient the colder it gets outside. So again, the language is the right choice to make now, but we will continue to refer to that kind of option as the best incomplete solution. Next slide, please. So this project began back in March. As Carolyn mentioned, we're so grateful for both the IESO and Enbridge Gas, and also for our industry partners, Carrier and HTS and Train, for stepping up to help us with technical advice as well as with funding to help this work happen. The mandate, the scope, the goals were we're looking to deliver a reference document, a decision-making guide to school boards that they can share with their project teams whenever you're considering replacing existing rooftop units at end of life or installing rooftop units on new schools. So this aims to be a complete and definitive document that can help you make good decisions today. It's applicable to rooftop units that provide the heating. So there are different solutions with air source heat pump boilers that supply hydronic heating systems, and we're going to be looking at that in future. But today it's the conventional gas-fired, typically with DX cooling. Rooftop unit replacement is the focus of today, which is the majority of the units going on to schools at this point in time. The guide addresses three areas. Why do we need to do this? And what do we do? And then how do we do it? So the aim is to work through those things. First, make the business case. Second, clarity around the issues, the technology, making sure we put the right size equipment in. Then the how looks a lot at utility prices, utility rates, the differential between gas and electric, and the variability, particularly in electricity rates over the course of the day, as to how do we best make the business case, and then how do we automate and control these units for the best economics on a go-forward basis. Before we go further, let me repeat Carolyn's comments. We see the audience here today as being a vital part of this conversation. We're not going to pretend to have all the answers today, but your input, your questions are really important. Use the Q&A, don't use the chat, because the chat is just for technical details. The Q&A becomes a file that we keep, and again, we will respond to questions that we can during the course of the webinar, and we will pick up on other questions we think are really important, both in terms of finalizing the guide, but also informally sending out answers through the website that you'll all be able to check in onto. So this is what we're trying to do. Next slide, please. And we want to put you to work immediately, if we may. This is a quick poll just for school boards. So I know industry government will be interested, but for school boards, and it doesn't matter if two people from the same board fill in the poll, but what we're really interested in, and what we're finding relatively little information at this point, is how many of your schools, how many of your individual schools have at least one operational air source heat pump now? How many years have they been in operation? And then looking forward, how many new schools are you opening, and how many older schools will have rooftop unit replacements in the next 5 years? And then a simple binary choice there. Are you considering air source heat pump? No, not at this time. Maybe I understand a little bit, but interested, and definitely I've made that choice. So Carolyn, could you pull that poll up right now? And we'd ask all the school boards on here. I say there should be over 30 of you. Please fill this in so we get an idea of the market the way it is right now. So about half has some operating experience with air source heat pumps, 45%. And a few have quite a few schools out there. So we've got some working experience. And how long have these been operational? So a majority of the ones that do have units less than 2 years, so it's fairly new. 2 to 5 years, we're up to 75%. So opening new schools in the next 5 years, more than half of you have at least one or two, and some a little bit more. And we're finding this a little bit. So that's new schools opening, and then rooftop unit replacements. Everybody's going to be doing some, and there's quite a lot there. So the replacement market looks as expected to be as the biggest piece. And we've got some decisive folks in here. More than half of you are definitely going to be looking at this, considering it at least, and 40% are on the fence, and 5% are no. And at some point, love to get comments in the Q&A on what would be the factors that would be within the no. But by the end of today, we hope to get to the point that we at least attempted to address some of the issues and the questions. And when we repeat this kind of poll 6 months or a year from now, we may see different results, and we'll refer back to these. But so as you know, well, Climate Challenge Network events, we almost invariably reach out to folks that have helped us both to get to the point that we're at right now, and also come across as leaders and having particular knowledge they'll share. And what we hear from school boards all the time is you're far more interested in hearing from each other than you are in hearing from me. Our panel today with again, with the background, the experience, the panelists will be Maurice, who many of you know from Toronto District School Board, which is also the subject of our case study, the Chester Lee School. Paul Prue, who we see Ottawa Catholic as a real leader. Ottawa Catholic has historically always been at the top of the Sustainable Schools rankings of the most energy efficient school boards in Ontario, and has a history for a smaller board of innovation with trying new things and wondering why everybody else isn't doing it. So, Paul, welcome to you there, and Mark Marty from Enterlife, who provide the technical support for this work and for the overall project. Mark has extensive conversations with our industry partners, who you see listed at the bottom, Raheel, welcome, and Curtis and Stephen, and Michael, the independent electric system operator. As you may know, we've just entered an election in Ontario, so Michael will not be in a position to give us an update, but we always appreciate your support. And we think it's Chris Chatley who'll be speaking on behalf of Enbridge Gas later as to where utility incentives fit into the screen. So this is the small part, if you like, of our expert panel. The big part is all of you out there in the audience. As I say, there are many other school boards here. Please do provide your questions, write them in. Carolyn tracks this very closely, and where you have a question that fits into where we are in the argument, in the storyline, we'll look to address it to one of our panelists, to one of our participants, one of our industry players during that time. And if not, again, we will pick up all the questions that get answered after this event. So welcome, panel. Thank you for being here. We will be referring to you on a regular basis as we work our way through the proceedings. And as always, Maurice, Paul, Mark, do interrupt me if I miss anything or there's something that you think is there. And again, we'll pick you up individually with respect to questions that come from the audience. So as always, thanks to the panel, not just for today, but for the time they spent preparing for this and with all the input over the last 9 months. Next slide, please. So let's get rolling. So again, this will not be new to many of you who are familiar with Climate Challenge Network's work. This 4-step process, and I'm going to ask you to forgive the repetition. It always begins with energy efficiency. We're too inclined to jump into decarbonization, electrification, major capital retrofits without making sure first that we're running that facility as efficiently as we can. And energy efficiency reduces not just energy consumption, the amount, if you like, of electrification that we have to produce, but importantly, peak demand. Peak demand in cold climates is going to be the driver of this whole transition over the coming years. So got to start with efficiency, get things running efficiently. Then we get to heat recovery. Then we get to renewable energy, and different people put air source heat pumps in either box 2 or 3. We put it in 3 because it is a renewable source. The heat comes back from somewhere or other. But renewable energy also includes geothermal, and we plan to look much more closely at that later this year. And then in the end, if the organization is committed to net zero, there's likely to be some residual greenhouse gas emissions at this point, that the market is emerging for carbon credits. Right now, they trade around $15 a ton. The prediction is, and there's some fairly big players coming into the market. The prediction is will be around $50 a ton by 2030. But right now, this is just another one of those uncertainties that all of you are having to manage through. But the steps should always be part of the conversation. We would welcome you just borrowing the slide and use it to kick off every one of these capital projects. Talk to your design team, to everybody involved there, saying where we are in the process and making sure that it all fits together to get you to that net zero vision, which is similar but somewhat nuanced for every individual school. So this is the pathway we're all on, whether we like it or not. Next slide, please. And Mark has done a fine job of summarizing energy efficiency. Obviously, there's a lot of details and a lot of sub-bullets under this, but these are the 7 areas of activity that can, again, reduce peak demand and as well as heating energy consumption. And the argument is we also need to be focusing on electricity demand and focusing on that at all times of day, on peak and off peak, and we'll talk about that a bit later, because reducing electric demand makes space for electrification. It allows you to run more electrification at more periods without adding to the province's, the grid's peak demand. So energy efficiency has never been more important as an essential precursor to decarbonization. The biggest single thing, and we recommend this to Enbridge and the OEB and the IESO at all times, we have to be moving towards every school across Canada having an up-to-date, in quotes, building automation system, remotely addressable, because you simply can't manage the thousands and thousands of individual buildings spread sometimes over big geographic areas without building automation. It's an absolutely essential tool. So it should be part of your capital planning to, within a few years, being at the point that every one of your schools is equipped that way. And we know many of you are working. Then the other 6 items here are all self-evident. They're all going to come up over the course of the day, but this is kind of your checklist. Have we taken care of this? Outside air control is probably the biggest single item. It drives that peak during the day, and proper control of that to make sure we've got good indoor air quality, but not excessive outside air in a cold climate. That's absolutely essential. And adaptive space heating, we'll show you in a moment. So-called optimized start, where things start early in the morning. Those peaks are very often where the big damage is caused in terms of peak demand, and they can be smoothed out with the building automation system and adaptive controls. But all of these 7 items we think are necessary as you move into this kind of decarbonization project. Next slide, please. And this begins with sustainable schools can help you with this. Every school has a savings potential number based on weather normalized targets. This is an extract from one school board's targets. You've got some schools that are relatively inefficient and have very high savings potential, either in thermal energy or electricity or both. And they typically have pretty large dollar savings potential, and they do have very big greenhouse gas emissions reduction potential. But every school board, we would advise All of those in Ontario, you have your sustainable schools. If you haven't contacted Carolyn or Katya, do so. But every year, we estimate the savings potential of every school in terms of gas, electricity, and then of all the boards, and then of the province as a whole. In other jurisdictions, happy to work with you on doing similar analysis for your schools. But going into any individual school for one of these projects, the starting point is how much room do we have for efficiency, and at least handling energy efficiency in parallel with the development of the heat pump projects. So every school has a rational target which dictates how much energy emissions can it save. And by getting that efficiency right as you're doing or preparing for an air source heat pump project, gives you a lot of flexibility around both the cost and the operation and the economics of the heat pump installation. Next slide, please. Right, let me stop there for a moment. Are there any questions that are coming out of the audience so far, Carolyn?
We don't have any in the Q&A at the moment.
Okay. And any moment now, Maurice and Paul will be looking to get this kind of back and forth working. As we touched a moment ago, the coldest week in cold climates like Canada, the coldest week is going to be the driver. So this is actually the week of January the 15th to the 21st last winter in the previous school year, and you can see in the orange how gas use, it's the scale on the left, and the blue is the electricity scale on the right. This is obviously off interval metering, and the cool thing is once you've got a functional BAS with that can export data, it's not that hard to convert the gas meter to provide this kind of information, and your electric utility should already have the blue data for you to run. And this should be part of the modeling that you do at the start of any one of these projects, like when do the peaks occur? And you can see here the peak is on Wednesday at about 10 o'clock in the morning in terms of heat. And you can see what electricity is doing in between. And this is Chester Lee School. And you can also see during the unoccupied periods, there's quite a lot of electricity being used here. And we'll look at that a bit more in a moment. So that's coldest week. And then within that time, the coldest day. The next slide, please. The coldest day becomes part of this. So it's exactly the same chart as you saw before, but this is more granular. You can see more issues. And what Mark's added to this is, as Ontario is looking at time of use type rates, we got off-peak periods up to 7 o'clock in the morning during weekdays. We got mid-peak periods during the day, which is where in schools most of the energy is used. It's not during peak periods. It's during mid-peak periods. Then on peak is that period from 4 to 10 in the evening. And we go back to mid-peak again, and we go to off-peak. These things matter because we believe and we recommend that over time we will continue to adapt our electricity rates and potentially in future our gas pricing to the times when the demand is highest, because peak demand again is going to become a big issue. So looking at how we're using equipment during the day, you can see what's interesting with Chester Lee on the left-hand side there, that first off-peak period. Demand picks up starting at 4 o'clock in the morning. And in future, that period is going to be important to us because that's when peaks tend to get made. And those are periods of time when we have the best potential for the air source heat pump if we have capacity to operate it. Next slide, please. And again, I think this is apparent to everybody, but the cooling and heating cycles, I think one of our industry friends on the project was kind enough to simplify it for my mind, which is It's just a rooftop unit with cooling with a reversing valve that allows it to go backwards in the wintertime. It kind of is that simple. On the heating cycle, we've got the gas furnace that's indicated here. And one of the big challenges for these installations is always going to be harmonizing the air source heat pump, the indoor coil, the coil that's pulling, that's delivering the heat to the air supply that's being pulled out of the outside air, coordinating that with the gas heating so that they work seamlessly together. You get everything out of the air source heat pump you can before gas comes on, and then gas comes on evenly in stages, so it doesn't kind of push into what the air source heat pump can be doing for you. So these are the principles. I love these simplified pictures, and Mark and our industry friends, thank you for this. And the next slide, please. Wanted to put this in here. We'll cover this again at the end, but and then Paul, if I may, and then Maurice, love your thoughts on this kind of early stage. What kind of modeling have your boards typically done for this? How is this kind of early stage work of the principles of the air source heat pump? What did that process look like? So I'll ask you both, if I could, for a bit of an overview of what your respective boards have been doing. But exhaust air heat recovery is obviously smaller than what the air source heat pump can do. Its real strength is it's working for you most during the coldest periods. So even though the direct economics, if we want to talk simple payback, we really have to be talking about electrification in terms of life cycle costing. But even though the payback of the addition of exhaust air heat recovery may or may not look attractive at this stage, that heat on the coldest days when the air source heat pump's no longer giving you heat will be invaluable. So we're big believers that if you can get the enthalpy wheel installed, and you can ask your suppliers and your consultants for premium costs, which you, with rooftop unit applications, you mostly can. But if not, any form of heat recovery that can take that heat that we're throwing out through the exhaust fans and put it back into the school, as we get to that peak load period in the 2030s, it will be invaluable to you. But this is a good pause point. Paul, could I ask you for a bit of an overview up front of the story so far, when it began with air source heat pumps, what your experience has been, how the business case was made, and then the same to you, Maurice, if I may.
All right, thank you, Ian. I can certainly give some history on the Ottawa Catholic School Board. In some of our previous discussions, I mentioned to the panel that our experience with air source heat pumps has been a long one. We've had several schools that we've been using air source heat pumps as the only heat source with electric backup, electric emergency, as we call it. We have schools that were built in the 1980s that we still utilize the same technology. We have a lot of our similar design elementary schools are fitted with 19 heat pumps. Some of them do a couple of rooms, some are dedicated to one classroom. We run the compressors on those down to -5. Most of them are controlled by building automation, and then we lock out the compressor below -5, and we switch over to electric duct heaters. Our retrofitting of air source heat pumps into our rooftop units probably began about 5 or 6 years ago. We've worked closely with different manufacturers, and it seems our desire to continue with heat pumps, our desire for carbon reduction, and then certainly one of the most driving factors for us is economics as well. We were steered in the direction of the air source heat pumps mostly because the upcharge for them isn't significant in the whole scheme of things. So we started with some retrofits early on with rooftop manufacturers. Our administration building where we are today, we replaced several rooftop units. We included heat pumps as well as a hybrid gas technology. So, we're running gas down to, we've experimented with different temperatures before we lock out the heat pump. We've recently built 4 similar design elementary schools using air source heat pump technology on the rooftops. And we're going to experiment with different settings on those to see what's most effective in terms of cost. We are noticing a significant reduction in gas consumption. Should point out we also eliminated boilers from our elementary school design. So, the schools that we're building now have 9 rooftop units for all the perimeter spaces and the gymnasium. The central core is heated with VRF technology, but the rooftop units do have air source heat pump potential as well. So we're running those, and we've compared the consumption of the brand new schools. We only had really 1 year of runtime on 2 of them, so it's difficult to compare right across the system. But we've noticed a reduction of 2/3 of our gas consumption compared to a similar design school that was built in 2019 without the heat pump technology and with the boiler in the building. So it's a significant amount. Now we do see an increase in electrical consumption, so the cost is almost revenue neutral. We don't see a huge difference. The money we're saving in gas is going towards the money we're spending in electricity. But I was expecting a huge upcharge in cost to run a building without a boiler, but we're not experiencing that at all. We're experiencing almost the same cost, which is very, very optimistic about it. We certainly have some tweaking to do on our setup. We're still going through some of the commissioning steps because these are brand new buildings. But I think if we continue to improve how they're operating, I think we're going to see we will see a reduction in cost and a drastic reduction in the gas that we're consuming.
Now, remind me, Paul, have you typically been specifying exhaust heat recovery on those units?
Yes, they all have enthalpy wheels for sure. Yes, and the areas of the school that are served by the VRF technology have a standalone dedicated outdoor air unit that we're finding. It's not equipped with heat, so it's just recovering exhaust temperature. And on recent -20 days, we're seeing a supply temperature in that unit of right around 12 degrees Celsius. So it's amazing that we can provide
That's great.
that, yeah, without any heat at all.
Yeah, thank you for that, Paul. Maurice, tell us the TDSB story.
Sure. Well, at TDSB, we have used air source heat pumps previously, but like Paul mentioned, these are VRF systems, so variable refrigerant flow, not what we're talking about today. The hybrid rooftop approach. So we've had a few of those projects in the past. So those work. But like any system, pros and cons. They also tend to be, from our perspective, a bit complicated to understand. And when something goes wrong with a VRF system, I think it really helps to have a good service contract in place because they're not straightforward from my perspective, right? To work on. So with respect to like Chester-Lee, which I think we're going to look at closer. That was an opportunity that we had because Chester-Lee did have a renewal need. The existing air handlers were the original from when that school was built in the early 90s. So the air handlers had to be replaced. And also Chester-Lee is typical of about 35 schools, all built within the same time frame. So they're all similar, same mechanical systems. So we thought, well, this is a great opportunity to try a hybrid air source heat pump system, work it through its paces, let's say, and then make a business case that we want to do all the remaining 35 schools in this way. So that's the process that we took. And so Chester-Lee, it is built, it is installed, and we're just about to go into the commissioning phase of that school, where we're going to have to work out, the strategies, controls, and all that.
Great, Maurice, thank you. Let's move to the next slide, and I'm going to come back to you guys if I may, and also I'm going to check in with Mark shortly to make sure we haven't missed anything. But next slide, please.
Before we jump forward, we do have a couple questions in the Q&A.
Yeah, fire
the
away,
first
please.
one from Mark Bedard. He's a school board in Ontario, asking, has there been an analysis of how the total cost of energy use, natural gas and electricity, of an air source heat pump compares to a standard RTU during all conditions during the heating season?
Very, very glad you're here. That's exactly what we're going to be getting into in just a moment. So if there's still questions outstanding after that, please go back to the Q&A and let us know.
And another question here for Paul specifically. The elementary schools with air source heat pump only, since there is no boiler, what or if anything is being used for heating backup in case of extreme cold weather? Also, had there been comfort issues without a perimeter heating system?
So for our new elementary schools with air source heat pumps, they're a hybrid rooftop, so they do have a gas-fired potential as well. So below a temperature that is adjustable through our building automation system or through the rooftop unit itself, we're experimenting with different temperatures currently, but we do lock out the air source heat pump below. Currently it's right around 0 Celsius. A couple of schools we're trying a little bit lower, and then it switches over to gas heat for that. So there is certainly backup heat for the coldest days. The VRF areas of those same schools, we do have electric baseboard heat in the admin areas and in the perimeter offices for the principal and the vice principal. Our common areas, like our learning commons and some of the corridor areas, we don't have backup heat, and we're finding that we're able to, with the VRFs that we're using, we are able to keep the spaces right around 21 Celsius. And we've had some cold days this winter. We've had some days here in Ottawa that the high temperature hasn't risen much above -20. So we are seeing that we're able to maintain heat in the common areas, and certainly in the classrooms we are using gas heat on the real cold days.
And your building envelope standards are higher for new schools now than they were even 25 years ago, right?
I think they're higher even than they were 5 years ago. We've upgraded our windows. We've added more insulation to the slab. We have exterior insulation now behind the sidings, and the brick. So yes, the roof insulation has been increased. So the envelope is much more robust. Yes.
And Mark, with your conversations with 3 major leading suppliers, that cutoff temperature, below which you say it's not worth running this, or you can't run it any lower, where have you found that to be? We've heard 0 degrees Celsius. I've heard -5 sometimes. What is industry telling you, and is it getting better over time, or once it's that cold outside, are you at the point that you're so close to a coefficient of performance of 1 that it's not worth running it anymore? What do you hear?
Yeah. Let me clarify one thing first, because there is something called fixed temperature switchover, which is as a balance temperature where a gas operation would start to be more efficient. However, there's a low temperature cutoff. I think this is what you're referring to, when the units can no longer run. And this is typically nowadays getting closer to -15 degrees Fahrenheit with the vapor injection compression that is being used with the latest technologies. So however, what comes out from factory as a set point for switchover between the secondary to the auxiliary heat stream, like the gas, typically it's between -5 and 2 degrees C. This is what comes out of factory. We've also heard that for some cases it's project dependent, depending on the heat load of the building and the application, and can go down to -15.
Fascinating. And that's been the history with residential, because these are quite different from residential units, but that low cutoff is improving over time, but still doesn't deal with the coldest day. And Paul, every time we hear electric heat, that kind of sets off little amber lights in our heads, because once we're winter peaking, that's likely to become quite expensive. So electric heat directly, um, we're not sure where that fits into the future storage for sure. But let's move on to the unless there's any other questions that have come up, Carolyn, let's move on. So the perversity of life and the air source heat pump in particular is the colder it gets, the less efficient the air source heat pump gets. I think everybody knows this. And again, this webinar is being recorded. It will be up on our website, so you don't have to scribble all these numbers down. All of that will be available to you, but you can see the issues involved. Where we looked at typically what the temperatures were like at the different times of day. So you can see, again, we're dividing this between on-peak, mid-peak, and off-peak. We get the best coefficient of performance in the milder months, October and May. And we're around, based on the equipment we looked at, and it varies a little bit between suppliers. But again, physics, the laws of physics are what they are. We're around 2.5, a COP of 2.5. So we get 2.5 units of heat out of these units for every unit of electricity that goes into the air source heat pump. So this is this again the inverse relationship between heating demand and the capability of the air source heat pump to provide it. Next slide, please. And again, we look to be very, as Mark said, everything is very school specific. Every project is school specific. But we looked at a range of units here, and what we're seeing is that in terms of the equipment, you're typically an 8 to 10% cost premium for the hybrid unit. And in case I haven't been cleared, we are recommending hybrid gas unit for as long as gas is available and affordable. So we believe that hybrid and the continuing use of gas is necessary to make this whole transition affordable. But looking for, in terms of equipment cost premiums around 10%, and total project cost premiums, because installation is similar, the curbs are similar, the electrical connection is similar. Between 5 and 10%, we expect that to be the cost premium between a standard gas-fired rooftop unit with air conditioning, with DX cooling, and an air source heat pump with the backup gas furnace. So 5 to 10% premium. Can you go to the next slide, please? And understanding the operating modes, and we'll look at life cycle costs in a moment, but we're going to be using language today which we commend to everybody around unconstrained operation is just letting the air source heat pump run whenever there is heating demand within the building, and irrespective of what the electricity price might be in that hour or what the electrical demand might be. What we developed Mark's modeling around the alternative of constrained operation, that we limit additional peak demand. So it's air source heat pump operation with demand limiting, which is also looking at the hourly electricity price. So optimizing it where the air source heat pump runs only to the extent that its electricity cost is equal to or less than. So, Paul's found some of that experience, but if you like, optimize control of the air source heat pump so you limit it during peak demand periods, which we believe will be helpful and required in future. It leads to a bit less heat recovery, but significantly lower electricity costs. So we're going to walk through that in just a moment and relate to the previous question. So the variables in constrained operation that are in the math, if you like, the algorithm by which you'll control the unit, obviously the outdoor air temperature is there, and it relates directly to the coefficient of performance. And January of last year, the average temperature during January was 27.9 degrees Fahrenheit. The COP was 2.4. The gas price in this case was 42 cents a cubic meter, and that varies across the province and varies depending on what contracts you may have. So the gas price is a variable. The hourly electricity price can range at times to be really, really low when the ISO's got more of it than they can deal with. So down to less than a penny a kilowatt hour to over $2 a kilowatt hour. So the electricity price moves around, and it can at times dominate this discussion about when is it economic to run the air source heat pump and when is it better to switch to gas. For January 2024, the global adjustment was 4.6 cents. And doing the math on the peak kilowatt, so we'll show you the model in a moment, but if you limit the additional peak to, say, 15 kilowatts over the norm and divide that by how many extra kilowatt hours that gives you, it adds about 2 cents. So the math at the bottom, and I apologize that we've tried to find a simpler way of representing this, is at 42 cents a cubic meter. If in the coldest weather, the electricity price is 10 cents or less, and in the milder weather, it's 15 cents or less, you're better off running the air source heat pump. If the electricity cost goes above that, you're better off switching to gas. So this is what we call constrained operation and related. So Paul, if I could just go back to you, I think the units you have right now at this point and are running in unconstrained mode, essentially, if they're running and overall it's not costing much of a premium. Is that about right?
No, we would be running in constrained operation. So we do limit the times that the heat pump operates based on outdoor temperature.
Okay, perfect. And Maurice, for Chesterlee, is this kind of math being built into the control logic for the Chesterlee units?
I'd love to say yes, but no, not yet. This is something that we'd like to, possibly work with folks like Mark on providing some guidance to us as to when is the best time, right, to switch between heat pump and gas heating.
Sounds good. Thank you. Let's drive on through this a little bit, because we believe that for our friends from utilities and government here, that managing rate structures can be a significant boost to without penalizing, without cross subsidization, to encouraging additional electrification going forward. Next slide, please.
We do have one question in the Q&A. I'm not sure if you want to address it now or later in the slides, but it's asking, can heat storage make sense for the systems at this time to deal with both peak rates and to deal with demand charges?
We believe storage is going to be critical going forward, that for electricity and gas, we're going to end up with on the coldest days, we're going to end up with, or the coldest weeks at least, we're going to wind up with nice plateaus. We haven't found storage options, and some of that will be centralized storage, and some of it will be site-based storage in individual buildings. We haven't found that to be economic, but storage, we think, is probably electric storage, we think, is the most likely way of dealing with these peak demands. So we think in-building storage 10 years from now will become the norm. At the moment, we can't make the economic case. And it's addable, but also the technology is moving forward, especially phase change. We're really intrigued with phase change storage, which we see coming into its own over the coming years. Meanwhile, rate structures, I touched on that a moment ago. This is the proposed non-regulated price plan time of use rates that the ISO has, the Ontario Energy Board has been contemplating, where the global adjustment will be varied by time of day, where at peak periods it'll be much higher, and during Off-peak periods, it'll be correspondingly lower. We like this type of structure because it lends itself to running it during the coldest times of day, during the off-peak periods, weekends, overnight, and running through. So this is just intended to illustrate the fact that regulators are looking at rate structures that can support electrification, and we commend the OEB for doing this, and look across all cold climates for this kind of work to help improve the economics. So it's easy to plug these numbers instead of regular numbers into the model and say, yeah, now we can run it longer, and with this rate we can get better. This will be an optional rate, and we'll be encouraging commercial building owners, school owners to adopt this kind of rate structure. Next slide, please. So if say the previous retrofit programs, so the ISO, Michael informs me that the energy retrofit program, I believe, still exists. And Save on Energy, you can check the website to look for what subsidies are available to help with the cost of this. So this is Ontario only, and we'll be interested in discussing with the other provinces represented on this call what kind of incentives they have, and we can provide that comparison. But with Enbridge, I'm not sure. Chris, are you going to speak to what Enbridge has today that can help with this kind of installation?
Yeah, sure. Beginning in this year, 2025, we are launching a prescriptive measure for hybrid heat pumps. And it's designed in a way where it captures a fixed incentive over a specific heating capacity. The ranges in heating capacity are below 32 kBtu per hour, all the way up to 200 kBtu per hour. And each range is the incentive ranges from $1,000 up to $8,000. There is an opportunity. There are specific requirements there that it is only what's not eligible for the incentive are split systems, standalone furnaces, makeup air units, and dedicated outdoor air systems. However, we will consider a custom incentive of up to $40 per kBtu per hour if some of the requirements aren't met. So that's new for this year.
That's helpful, thank you. And it becomes a significant part of the math, the life cycle cost analysis. We'll show you some of these numbers when you run this all out over a 15-year period in just a moment. But thanks for that. And you can expect both utility rates and incentives to be evolving fairly rapidly as the whole energy transition gathers steam, as it were. Next slide, please.
One quick question here from Laura at Appleby College asking, are incentives for retrofits only? What about new builds?
Great question. Chris, can you speak to that?
Yes, this is for both retrofit and new build.
Thank you. Next slide. So the simplistic world that energy efficiency has tended to occupy, a simple payback, it just doesn't work when you're talking about major capital projects that have a life of 10, 15, 20, even 30 years. So get used to the idea of life cycle costing. When school boards, you're talking to your consulting engineers, make sure that this is what they're offering so you can look at options. Because if you look at that little box in the top right-hand corner there, everything there is highly variable. So inflation changes, the escalation of utilities. This model, I think, is understated, both in terms of electricity and gas over 10 to 20 years. But inflation changes, but the end model here, which allows you to play with these things so you can do your own risk analysis to help decision making, is the green dotted line here is if you like so the yellow line is if you just buy a regular gas-fired DX cooled rooftop unit. The yellow line is the economic picture going up to for 15 years to 2040. The green dotted line, you can see the cost premium at the beginning. It's just a bit more expensive. And it crosses with these assumptions at about 10 years. And this is a 10% cost premium that we've allowed it for here. If you put a 5-year cost premium, the break-even point is almost immediate. So we played around with lots of different assumptions, what the ranges might be. And we believe there are very few scenarios right now where it doesn't make economic sense on a 15-year period to use rooftop units instead of, SOS heat pumps instead of conventional rooftop units. But you need this kind of modeling and to play with your own factors, your own project, your own sensitivities to be comfortable that you're making the right business decision today and paying a little more for positioning going forward. Next slide, please. Then how do you put all this in? So all of this will be, again, available to you on the recording, but one way or another, the roof openings may or may not lend it to it. The electrical capacity matters. Chester Lee was good because it used to be an all-electric school back in the day, so it's got lots of transformer capacity. Demand management matters, so you may extend the life of the equipment as well as optimizing utility costs. Adaptive control is how you smooth out those startup peak heating demands in the morning, making sure your staff are comfortable with this. So all of these issues kind of matter. The next slide, please. And the sizing the units, you've got the peak electrical demand, you've got the peak cooling demand. In the perfect world, they match reasonably well. That the size of the compressor condenser for cooling does a pretty respectable job for the air source heat pump. Again, the dual fuel, we believe that hybrid is here to stay for the coming years and is the right approach to take. Modulating controls, this ability to control smoothly between air source heat pump operation and gas operation without them fighting each other, overlapping. And typically, we're not finding a lot of issues with rooftop unit applications around structural capacity of the buildings to take them. But these are all considerations you should be discussing with your design team as these projects proceed. Next slide, please. We talked about exhaust air heat recovery already, and we like this little winky wonky model as things bounce around. But what Mark did with this is the unconstrained operation here, that yellow box second from the right, would take us up to a peak electrical demand of 164 kilowatts. The constrained operation keeps that down to 105 kilowatts. So we'll look in a moment at, we don't lose that much heat recovery, but we do really good things for the grid. So this model of moving step by step from baseline gas use on the left-hand side to adjusting for domestic hot water, because in this case, it is staying gas heated, through energy efficiency and through then the air source heat pump. This we found to be a helpful way of stepping through. How much heat can we still recover without imposing undue demand upon the grid? Next slide, please. We're not covering now air source heat pump boilers, but that's the similar technology producing hot water to inject into hydronic systems. We'll be looking at that in future. Next slide, please. There are air source heat pump domestic hot water heaters. We're not finding them for the volume used in schools. We're not finding them cost effective right now. And I don't believe that either Ottawa Catholic or Toronto District is using them at the moment. Solar PV, this is a good time to do this where solar PV can reduce in the winter electrical demand and make room to run more of the air source heat pump. So you get kind of the double benefit. You get the electricity produced by the PV, and you also get more use of the air source heat pump. So this we find intriguing. We haven't found a working installation of this yet, but we will be. Next slide, please. And again, we could have a whole webinar on this subject as how to control these units, and perhaps we will at some point. But the ability to control the units, both at the high level, that transition between electric and gas heating, and at the more specific level, this idea of dynamic controls, smart integration, all of that kind of language, which at the end says, if we optimize the air source heat pump, we can get the best gas displacement, fossil fuel displacement results at the least electricity price. And that is worth doing and exploring. And as these kind of algorithms get perfected, we look forward to sharing those with everybody in future. Next slide, please. If you can run a rooftop unit, you can run these units. They're obviously the compressor condenser are going to run more than they would with a conventional unit. The defrost seems to be the biggest issue that we've heard so far, is one, optimizing it so that it doesn't cost too much, but making sure that the water that comes off that in the middle of winter doesn't end up in places where the ice is going to cause some damage. So the only significant operational concern we've seen so far has been around defrost, and these notes, I think, Mark, capture this really well. Next slide, please. And again, it's always nice to see what these things look like in reality. And we, the Chesterley case study, it's at the commissioning stage, as Maurice mentioned right now, so we haven't yet seen the full potential and performance, but we will over the coming months. But just very generally, you can see the school in the picture at the top. There's a daycare on the left-hand side that did not get converted to air source heat pump. The 2 units and the one on the right-hand side in the gym, those are the 3 units that were put in. These units are very atypical. These are multi-zone air handlers back in the day, so it's not like a normal rooftop unit conversion, but it's a wonderful example of tracking through these steps within the whole process. The school does have a boiler plant. The boilers lend themselves to the significant load variation as the air source heat pumps come on and off. There was no exhaust air heat reclaim in this particular case. The electric feeder looked fine, and domestic hot water is not served through the air source heat pump operation. So here's our school, and I'll just go fairly quickly step by step, and then at the end I'll be going back to Paul and Maurice to comment on recommendations. What should people be looking out for, and so on, based on everything we talked about today. But here's the Chesterley School, again, installed, going through commissioning, results to follow, and we're more than intrigued to see how that turns out. Next slide, please. So again, you can see some of the background math and the units. It's about 100 tons so the installed capacity of the 3 units is around 100 tons, as is shown there in note 5. In the coldest time, we get about 720 MBH of capacity out of it. And again, with this is the kind of analysis to say, what is this unit actually going to do in this specific application? Next slide, please. Maurice mentioned this is all of the so-called SEF schools that Toronto District School Board has. Then you can see the ones at the top are less efficient. They have much bigger savings potential. The ones at the bottom are a lot more efficient. Some of them are in greens, which means they're pretty close to energy target already. This particular school has a 52.1%, you'll see, electricity savings potential, and I think a little over 60% on on gas, so it's fairly intensive in gas use. And going through the analysis, you can see where the extra electricity and gas is being consumed. So the energy efficiency part falls into play there, but there's $46,000 a year of utility cost savings potential before applying the air source heat pump. So this is the kind of starting point around energy efficiency. Next slide, please. And we wanted to share some of the latest trend. This is from yesterday, sorry, the screen captures from the units. You can see yesterday it was minus 1.1 degrees Celsius, and we were interested, Maurice, that the air source heat pump wasn't running and hadn't run yet, I think, this week. So this cutoff sounds interesting, but again, it hasn't been commissioned yet. Is that correct?
That's right. So my understanding is that it's had very limited, if any, operation at all, and it's waiting for commissioning to take place. So hopefully, if that progresses well, we're going to be able to see the operation during the remainder of the heating season.
Right. And this was about 7 o'clock yesterday evening, and you can see here, if Carolyn could move the cursor to it, the units were running. They got variable frequency drives on the fans, which is great. In the evening, you had 442 parts per billion. So that's a fairly low concentration, but everybody's gone home by then. We looked at the runtime down there before. Mark just quickly ran the percentage outside air calculation based on the outdoor air temperature, the mixed air temperature, and the return air temperature. So the unit at that time was running about 21% outside air, and the damper was set at about 28% outside air, and we know that relationship. I had thought, Maurice, that TDSB as a standard was showing that calculated percent outside air on your screens. Is that not the case?
It should be. So we actually calculate. I think it's reading 0 again. Pre-commissioning.
Okay, so that's what that 0% is.
Yeah, so that's what that is. It should be reading what the actual calculated OA is. Yeah.
Terrific. So that would be 21.2 in the future. The second unit is the gym. If we can go to the next slide, please. And a few things we liked here. We like you got a variable speed drive on the supply fan, no return fan. But during unoccupied periods when you need the unit for heating, it's nice to be able to run at a lower speed and save a whole bunch of electricity overnight. The Mark picked up, do you see that the return air temperature at the top is at 10.6 degrees Celsius? Obviously the fan's not running, but that would suggest there's outside air leaking in through the relief air dampers or the outside air dampers, or both, depending on where the sensor's located. It'd be good to have the commissioning folks take a look at that, say, are the dampers closing nice and tight? But we love that you've got the occupancy sensors in there. I'm sure many of the boards on this call do, but occupancy sensors in gyms make perfect sense. So a lot of things to like here in terms of the energy. In this case, this unit has been running already, ran a bit last week and has run a bit already this week. So you got some operational experience. So everything up and running.
Just a note, I was going to say that this, I think you mentioned, this is a very atypical system.
Yeah.
So this is a building that already had existing boilers that were actually replaced in 2019. So we had a new boiler plant with piping to all the existing air handlers that got replaced. So this is why you see hydronic heating coils, not gas fired, because that's what we had to work with. But hydronic heating, actually, from the point of view of controls, is actually better, because you will be able to fine tune the supply air temperature to whatever we want. So it's actually a bonus for us.
So next slide, please. So again, conscious of the clock, but this is picking up for Chester Lee on electricity pricing, as it says. Part of the electricity bill is fixed, same monthly charge, but the most of it is variable based on either demand or consumption. The hourly electricity price varies through the day, and this would apply to every school. So this looking at your electricity rates for your particular LDC or distribution utility at the time becomes part of the math. Next slide, please. And looking at how that demand varies. So this is picking up the actual kilowatt demand at each hour of the day on average between the different months of the year. And once again, off-peak, mid-peak, on-peak. During the off-peak periods, you should be able to run the unit pretty much flat out based on heating demand, but you'll still be optimizing it to make sure you don't go over the peak demand that you set within what we're suggesting should be a demand limiting algorithm within your building automation system. During the mid-peak period, which is most of the time when the school is running, again, there are periods of time there where it makes sense to run it flat out. There's periods of time when it makes sense to switch it off. The on-peak period is the most expensive. So with time of use rates, you'd be not running it very much, but there will be occasional moments. You can see there's times there where the color's a bit lighter and so on through. So this idea of if we're on time of use rates, off-peak, mid-peak, on-peak, can be your strategy for optimizing electricity use, demand, and costs. Next slide, please. And we just ran this model for interest. During unconstrained operation, you can see these are the times when most of the gas offset takes place. So the coldest months, the middle of the day, those are the periods of time when the biggest opportunity is. And again, if you've got interval data, which is available to you both electrically and gas these days, it gives you the opportunity of kind of mapping this and saying, how do we optimize how much heat we get out? And that's the key answer, because the next slide, please. So the unconstrained operation at the top during the 3 periods of the day, they generate that 34,194 cubic meters of gas displacement, which is most of the gas use. If we look at the constrained operation where we limit the extra demand to just 15 kilowatts, so if we go above that demand, it slows down or shuts off the air source heat pump, we still get 84% of the emissions, if you see that in the bottom right-hand corner. So you can get most of the gas savings without unduly burdening the electrical grid or adding to your electrical charges. So the good news is most of the gas we can eliminate running it more economically. Next slide, please. Again, the rest of this you can find on the recording for the deck, but on the left-hand side there, it's what happens between unconstrained and constrained for electricity use, for gas consumption, and on the right-hand side for the costs. And we can save money by running in constrained mode. And then as rates and circumstances change over time, that model is readily updatable to say, what's the optimal operating strategy? Next slide, please. And this is similar to the picture that we saw before. In unconstrained mode, we've got more electricity at 230,000 kilowatt hours, and the gas is pretty much gone. I think we're left with 164. Then the constrained mode beside it, the gas creeps up to 22,000, but significantly less electricity consumption. And once again, that key thing, 167 kilowatts peak demand, unconstrained 105 kilowatts, constrained. Next slide, please. So that is kind of the meat of the story we wanted to share with everybody today. We got our conclusions and recommendations. I can run very briefly through those right now. And again, spoiler alert from the beginning, we think this is the smart thing to do today. With everything considered, all the uncertainties, the energy transition is coming. We need to start electrifying. This is the smart move to make that's most economical, if you like, low risk, starting from now. So everybody who at the beginning had new schools that may have rooftop units or replacement rooftop units, our advice is, subject to looking at the details of the particular school, is look seriously at air source heat pump technology. It takes you a big step and it takes a major cut into greenhouse gas emissions. And we simply, going back to our beginning slide, we just got to do this, and we've got to do it sooner rather than later. Don't forget to make the schools energy efficient first. So look at the schools that are planned for rooftop unit replacement in the coming years, and prioritize them with your energy efficiency work. Hybrid, we recommend. Look at heat recovery and make sure you apply it wherever you can. Look at renewable energy options, and talk to your consultants and equipment suppliers around smart control algorithms. So if I may, Paul, can I go back to you with if your closing thoughts in terms of what you've heard today, your excellent experience over the past 5 years, what were your closing thoughts to the other school boards on this, Colby?
Well, I think maybe similar to what we see on the slides that Maurice has prepared. Commissioning is critical. I think there's a lot of parts that need to be verified when we are commissioning these hybrid systems. We commission heat, we commission cool, but we don't necessarily, we haven't in the past been commissioning as to when we're heating with electricity or when we're heating with gas. So that step gets missed during the standard commissioning process. So we're finding we're having to go back and revisit that sometimes a couple of months or 6 months after the school has opened to ensure that what we think is happening is actually happening, because it's very difficult to tell on an automation graphic what is actually running. It requires a bit of work to get into the BACnet network on these units and view things in a text form rather than in a graphic form. And certainly our building operators aren't doing that, so we're finding we're having to go back and just have our staff here in the office verify that we are in fact operating the way we think we are. So that's a critical step, probably much more critical than regular commissioning. In terms of lessons learned from our board, I think we're very happy with the hybrid gas rooftop units. I think we'll certainly continue with that. We're seeing efficiencies. We're not seeing a huge cost increase in procuring them or operating them. VRF technology is probably, we're a little bit more on the fence on that. We have introduced VRF now in several schools, and we're continuing to convert some of our older style of heat pump schools to VRF. But we are seeing significant cost to that. So we may pause on that, and take especially with the changes in refrigerant and how that might change that whole sector. We may pause on installing further VRF units until we have a better understanding of where we're going in terms of whether they are cost effective and how much more cost effective or less cost effective it might get as refrigerant rules change in Canada.
Excellent. Maurice, could I turn to you for your closing thoughts, the words from the wise?
Well, the units at Chesterly, this is the first pilot where we're implementing this. Those units were around for 30 years. Right? So we're replacing these units, and hopefully they're going to be here for 30 years at least. So what's going to happen in 30 years' time with respect to hydro rates, gas rates, carbon taxes? Who knows, right? Obviously.
Yep.
So what we found is that the premium to go to a hybrid approach rather than a standard straight rooftop replacement, as you mentioned, 5 to 10%. So it's not a big premium to pay. At Chesterly, those units were actually sized for the previous cooling capacity of that unit. So the retrofit was very straightforward. So there was no additional electrical requirements. We had all of the existing hot water lines in place. So really, it didn't really complicate that project much at all. So we think it made sense. We're very interested in getting some of the analysis done after the commissioning takes place. But I would think that when we tackle additional schools that look like Chesterly, and we have a lot of them, that it's going to make sense to follow this approach.
Perfect. So let me just, as we come to the end of this, Maurice, Paul, and Mark, thank you so much for taking the time to do this. Again, your practical experience is invaluable. Can we just go to the next slide, please? So next steps, if anybody's heard anything today that they feel strongly about, we've just got a couple of days where we'll be open to email comments, questions, concerns that can be factored into the guide. We will be publishing the guide the first week in February, and it will be up on the Sustainable Schools website along with the recording of this webinar and available to anybody and everybody that would like to be reminded. Stay in touch with us, stay in touch with Sustainable Schools, stay in touch with your experiences. As this works through, we'll be following both Ottawa Catholic and Toronto District, and we'll have update bulletins from time to time to keep everybody involved with what is a fast-moving agenda as far as the energy transition is concerned as we move to further into 2025 in June. Stay tuned for we'll be ranking again all the school boards that are willing to share their data with us from across Canada, but certainly all the boards in Ontario with the publicly reported data. So which are the most efficient schools? And once again, a panel discussion, what are they doing differently? And look out as well, what we do see as addressing this peak is geothermal. We've had very mixed experience with geothermal across Ontario over the decades. We've got some great success stories. We've got some horror stories. And our intention is to, again, work with industry to pull the geothermal story together around best practices, case studies, and again, an application guide that we can share with everybody to say, based on what everybody knows right now, this is the best of what we've got right now. So geothermal does address those peak weeks and peak days. We think it's important, and we'll be working, as always, with school boards and our friends in industry and utilities and governments to help make it happen. Final slide, please. These are our contacts. Mark, you heard from today. Carolyn, you heard from today. They're on top of this around sustainable schools and all of our research that's going on. So thanks as always to them. The front person on all of this, that's where all the work gets done. And thanks to everybody on the call for taking the time out of your busy days to join us today. Hope you found something useful, and we look forward to hearing further from you in future. Thank you very much. Have a great day.